Okay, time for the first of our strange words for this unit, and that would be enthalpy. Okay, so as we've already discussed, chemical changes can involve the release or the absorption of heat, negative Q or positive Q. There can also be work done on the system or by the system, positive W or negative W. The work is often either electrical or mechanical work. We're usually going to be focusing on the expansion of gases, and that falls under mechanical work. So, mechanical work done by a system involving expanding gases is called pressure volume work, or PV work for short. So, the heat transferred between the system and the surroundings during a chemical reaction, if it's carried out under constant pressure, is called enthalpy, and it's symbolized with the letter H. To really simplify it, enthalpy is just a fancy way of saying heat. Okay, enthalpy is the heat that's transferred at constant pressure. Now, it may seem like it's hard to do a chemical reaction at constant pressure, but it's not. All you have to do is perform the reaction in an open container, and the pressure of the room, unless you're in a really strange scenario, the pressure of the room should remain fairly constant, okay, barring a coming thunderstorm or tornado or something. So enthalpy, when you see enthalpy, just think heat. All right, so we can measure the work done by a gas if the reaction is done in a vessel that isn't in an open container. Okay, if it is in an open container, then the gas is just going to bubble away, and we can't really determine much about it. But if it's done in a closed vessel that is fitted with a piston, like we've been dealing with for a while now with the gas log unit and such, we can actually calculate the work. Work is equal to the negative of the pressure times the change in volume. Okay, so delta, the Greek letter delta right there, it's a capital letter D in the Greek alphabet, just means change. So final minus initial. The final volume minus the initial volume gives us the change in volume. If we multiply it by whatever the pressure is, the negative of the pressure, that'll tell us the amount of work done. Why is this negative so important? Well, remember, if the system does work, then work will be negative. So this is here so that we'll have a negative answer when we're done if the system did work. If work was done on the system, then the system was squeezed and we have a negative change in volume. It decreased in size. So our negative change in volume times our negative pressure, negative times a negative, it'll give us a positive W, like it should have if work was done on the system, if the gases were squeezed. So a scenario like this, we saw an image like this in the gas law unit. If we dump some zinc into some hydrochloric acid, it's going to bubble and make hydrogen gas, and that gas is going to expand and push the piston up. Okay, so we can measure the change in volume and then multiply it by the pressure of the room, because just like in our gas law experiment, the pressure pushing down on the piston is equal to the pressure of the room, so we can infer the pressure of our system that way. All right, so that's pressure volume work. Okay, so if it increased in volume like this example does, then that means the system did some pressure volume work. Okay, and we'll get a negative answer there. If the system does work, just look at it like you are the system. Okay, do you want to do work? Neither do I. Okay, so it's a negative thing if the system has to do work. Okay, if work gets done on you, like you get a massage, and somebody's doing all the work on you, well, then that's a positive thing. That's how I keep it straight. All right, so pressure volume work again. Here's another piston. Okay, this is all fancy, but it's just showing the change in volume. Okay, we would take that times the negative value of the pressure. So when a process occurs in an open container, commonly the only work done is the change in volume of the gas pushing on the surroundings, or being pushed on by the surroundings if work is being done on the system. So you'll have some piston problems with this stuff again. All right, so constant pressure, as I said earlier, is easy to achieve in the lab. Just do the reaction in an open container. The pressure is equal to room pressure. So when you look at this picture, you may not see that as an open container, but this piston's movable, okay? So that counts. All right, so again, we can only measure the change in enthalpy, just like we can only measure the change in energy. We talked about getting delta E is simply Q plus W in the previous section. Same thing here. There's no way to stick a probe inside the little molecules and figure out exactly how much energy they have at a given moment. All we can do is figure out how much energy they've gained or lost. Same thing with enthalpy. We can only measure the change in it. We can't determine exactly what the initial enthalpy was and what the final enthalpy was. We can just calculate the change. So remember, delta E equals Q plus W. So since pressure volume work is small for most reactions, generally what we're going to be doing is saying that the change in energy is equal to just the Q. Okay, if there's no gases formed, then there was no work done. So you're only going to have Q. You're only going to have heat being gained and lost by the system. And when that's the case, the enthalpy is going to be the same as Q. All right, so when we're dealing with calculating the enthalpy or the delta E, if the reaction doesn't produce a gas or anything, then there is no work. All there is Q. So the heat, the Q, is equal to the change in energy, which is also the change in enthalpy. So the heat transferred from the surroundings to the system, just like Q, it's going to be positive. If heat goes into the system, that's positive. If heat exits, if it loses heat, then that's negative. So if it's an endothermic reaction, heat enters the reaction. So that's a positive Q or a positive delta H. Now, it sometimes messes with people because if you take, say, baking soda and vinegar and mix that together in a sandwich baggie and you feel it, you touch the bag, it feels cold. And that seems kind of counterintuitive to people, but remember, that's an endothermic reaction. Heat enters the reaction. So the system is the baking soda and vinegar in the baggie. You're part of the surroundings. So the system, the reaction between the baking soda and the vinegar, sucks in heat. Well, where does it get the heat from? You. And you feel that loss of heat as cold. Okay, that feels cold to you. So endothermic reactions are sucking in heat, but to us they feel cold because we're not part of the system. All right, now if heat is transferred from the system to the surroundings, like the magnesium and the hydrochloric acid that we did in the gas law lab, that actually released heat. That would feel warm, okay, because heat's exiting the reaction and going into the surroundings, and we're part of the surroundings, so we would feel that as heat. Now, state functions, going back to that again, state functions are simply properties that don't, changes that don't depend on how the change occurred or how many steps it took for that change to occur, whether it happened in 1 step or 5 steps, the overall change is going to be the same. That's a state function. It doesn't matter how you get there. It's going to be the same change, the same difference either way. So enthalpy is like that. Some chemical reactions you can do all in 1 step, but in other settings, the reaction occurs in several mini steps. Either way, the overall enthalpy change is going to be the same because enthalpy is a state function. All right, so here's a sample problem. Indicate the sign of the enthalpy change, the delta H, in each of the following processes carried out under atmospheric pressure. It's always going to say carried out under atmospheric pressure. Don't let that confuse you. That's just meaning there's no work happening here. All we're worried about is Q. Q is going to be the delta H. And then indicate whether it's exothermic or endothermic. So an ice cube melting. Okay, it's going from a solid to a liquid. It's going from a low energy state to a higher energy state. How do I know that? Well, in a solid ice cube, the molecules are fixed in one spot. They're still jiggling. Okay, the jiggling happens all the way until 0 Kelvin, absolute 0. So the molecules are fixed in one position and they're jiggling in an ice cube. But once it's melted in liquid water, the molecules are slip-sliding around on each other and they are moving quite a bit. So where did all that extra energy come from? Okay. In order for an ice cube to melt, as you already know, it needs heat. Okay, that's what the heat provides the molecules with enough motion, enough energy to break free of each other. So heat must have entered, energy must have entered the ice cube in order for it to melt. So that would be endothermic. And then because heat entered the system, the ice cube, that would be a positive delta H. All right, in B, you might be able to see it because of my little screen here, but 1 gram of butane is combusted in sufficient oxygen to give complete combustion to CO2 and water. Okay, butane is what's in lighters, so a gram of the liquid in a lighter is burned. Okay. That's obviously going to release some heat, okay, so that's exothermic. Heat exited the reaction, and so because it lost heat to the surroundings, that would be a negative delta H. All right, so there it all is in words if you want to see it there. The water in the ice cube is the system. It absorbs heat to melt, so positive delta H, endothermic. The butane burning, negative delta H because heat is released. It's exothermic. All right, now we are going to be given enthalpies of reaction. You're going to determine enthalpies of reaction in some labs that we're going to do, but a lot of times the enthalpy will be stated. There's a big table in the back of your book with all kinds of enthalpies, and you can do stoichiometry with the enthalpies, so yay for stoichiometry. So for a reaction, once again, we can only look at the change in enthalpy. So the change in enthalpy is simply the final enthalpy minus the initial enthalpy. So the final enthalpy is the enthalpy of your products minus that of what you started with, your reactants. So the enthalpy change that accompanies a reaction is called the enthalpy of reaction. Or sometimes it's simply just called the heat of reaction, because remember, if the system's not doing any work, the enthalpy is just Q, and that's the way it is going to be for us. So the shorthand way of writing heat of reaction is delta H and then RXN for reaction. All right, so consider the thermochemical equation for the production of water. Oh, that was a big word. Thermochemical equation. Thermochemical equation just means a chemical equation with the energy written next to it, okay, the enthalpy written next to it. So this is the equation for the production of water. We got hydrogen and oxygen producing water, and every time this reaction happens with these ratios, 2 moles of hydrogen, 1 mole of oxygen, and producing 2 moles of water, that equates to 483.6 kilojoules. Sorry if you can't see the J there. That much energy is released. So what I want you to do, you can see this little plus sign that I wrote in there from back in the day when I had a smart board. I want you to pretend that this delta H is just part of the products, okay? So hydrogen plus oxygen makes water and this much energy coming out. That's all that negative means. So when you see a negative enthalpy or a negative Q or any of that, don't think of it as like a mathematical negative, like a minus sign or anything. Just all that negative is doing is indicating the direction. Negative means it's exiting the system. Positive means it's entering the system. So just pretend it's part of the balanced chemical equation. If you look at it like that, it's really easy to do these problems. So this equation just tells us that 483.6 kilojoules of energy are released to the surroundings when we form 2 moles of water. Now, this enthalpy corresponds to these coefficients, okay? As I said, it's just like part of the balanced equation. So the delta H depends on the number of moles of the reactants and products as written here. So this is for the formation of 2 moles of water. If we were wanting to make 4 moles of water, it would just simply be twice as much. So guess what this means? Because this number here, this negative 483, is tied to these coefficients, that means we can do a conversion factor with it. We can do like a mole ratio, but instead of going mole to mole, we're going to go mole to kilojoules. Yay, more stoic. Okay. So, all right, now before we get into doing those, oh, I'm out of time. Pooh. Okay, well, we will study this crazy diagram here in a second.